Hello everyone, I am Pushpita Chanda. I am a TA for this session for Introduction to Laser. Uh, I am a PMRF scholar at IIT Delhi. So let us start today's lesson. So first, let us discuss something like Fabry-Perot resonator and the longitudinal laser cavity modes. So Fabry-Perot resonator, or we can say that two mirror their cavity. So having the mirrors at the each end of the cavity leads to a development of both longitudinal and transverse modes superimposed upon the beam. So, okay, these modes produce both longitudinal, that is frequency dependent, and transverse, which is special dependent characteristics of beam. So we will first obtain expression for the longitudinal modes based upon simplified consideration of an infinite plane wave operating within the laser cavity. Then we can see the leads to construction of spatial profiling of the beam using spatial modes or transverse modes of the laser beam. So that এখানে গেলে within a cavity a radiative thermal equilibrium is reached. So similar modes development also within the laser cavity with similar boundary conditions such that electric field must be zero at the reflecting surface of the mirror. So therefore our analysis by considering what happens when a beam of light is incident upon a two mirror cavity, which is known as Fabry-Perot resonator with no optical elements between the mirrors. So then we consider the effect of placing an amplifying medium between the mirrors. So first we consider So before I start, now February interferometer Italian analysis. I want to um, uh, establish some relation between coefficient of reflection and coefficient of uh, refraction, transmission, coefficient of reflection and coefficient of transmission. So for these are known as, we can also call them Stokes relation. So now we investigate the reflection of light at an interface between two medium using the principle of optical reversibility. According to this principle, in the absence of any absorption, the light ray that is reflected or refracted will retrace its original path if its direction is reversed. Okay. So, so consider a light ray incident on the interface of two media like this. So a ray traveling in a medium of refractive index N1, that is N1, where in N2, from the ray is traveling from a medium of refractive index N1 to of a medium of refractive index N2. So the amplitude, reflection, and transmission coefficient bit in a reflection coefficient and transmission coefficient are R1 and transmission coefficient is T1 for in one medium, and amplitude of ray is so this is the ray A reflected, so it will be R1, and this is transmitted, so it will be A T1. Okay, the we like the reversibility principle says that in the absence of any absorption, a light ray that is reflected or refracted will retrace its original path if its direction is reversed. The reversibility. So here we have seen the ray of amplitude E1 when fall on an interface of uh, two media of refractive index N1 and N2. Part of the ray is reflected, which become AR1, and part is the transmitted, which is a T1. Now we reverse the rays and we consider a ray of amplitude T1 incident on medium. So our ray T1, A T1 will fall on the interface of the medium incident of the interface 2. So this is a R1. Now part of this ray will be reflected and part of transmitted. So this will be a T1, T2, and it will be a T1, R2 because of reflection. So the T1 R1 configuration comes from if the ray originated like in from medium 1, so that is like R1 T1. Then if it is coming from 2, like it is medium 2, it is medium 1, so it will be like R2 and T2. Okay, coefficient when the ray is incident from medium 2 on medium 1, then it is R2 T2, and when R1 T1 is when the ray is incident from medium 1 on medium 2. Okay, R1, so the ray is coming from 1 and remaining 1, so it will be a R1 square, and this will be a R1 T1. Okay, let me write. Figure 1. and 2, as we have already stated, that we need to use the optical reversibility principle, that if the and assume there is no absorption, so a light ray that is reflected or refracted will retrace its original path. So A will be equal to, compare, if we compare that, A will be A T1 T2 plus A R1 square. Okay. On it, A T1 R2 plus A R1 T1 is 0. Okay. From this to relation, from this, that 1 is equal to T1 T2 plus R1 square. So T1 T2 will be 1 minus R1 square. And from this thing, we can see that R2 plus T1 R1 will be 0. So, which means R1 is equal to minus R2. So, T1 T2 can be equal to 1 minus R2 square. Because R1 square is equal to R2 square. Okay. Relation number 1 and 2. Relation 1 and 2 called or are known as Stokes relations. Okay. Now we'll move on to the actual calculation of Frederick Weber Italan. Okay. The basic thing that we have assumed, like that when a ray traveling from medium 1 to medium 2, then R1 T1, and when it is traveling from medium 2 to medium 1, then it R2 T2. So we values, that is 1 mirror and mirror 2. And first we assume that this is N1 medium, this is N2 medium, this is N1 medium. Okay. And on here, so N1 is equal to N2 is equal to 1. The gap between this is odd, T, whatever you are comfortable to assume. So this is a light of amplitude A naught incident on a interference of medium 1 and 2 A naught. Part of this will be reflected A0 1, and part of it will be transmitted A0 T1. Part of it will be A0 T1, A0 T1 R2, and it will be A0 T1 R2, then it is transmitted T2, and e to the power I delta. I will like this and will transmit it and then it will be reflected. The next ray will be E0 T1 R 2 T2 and this will be R2, then R1 and so on. So this will be A0 T1 R2 whole cube A2 e to the power I in delta. It will be here A0 T1 T2 R2 square e to the power I delta will be A0 T1 T2 R to the power 4 e to the power 2I delta and so on. So the reflected beam amplitudes are one A0 T1 R2 T2 e to the power I delta A0 T1 R2 whole cube T2 e to the power I delta A0 T1 R2 to the power 5 T2 e to the power I delta and so on. So for this consideration equal to N2 is equal to 1, R1 is equal to R2 basically because the medium is same, but we can assume that for general consideration N1 and N2 will not be same because in laser there will be a gain medium, so N2 will be different. So that's why we are like taking the consideration of R1 and R2 is different. So the resultant will be AR summation of all those A naught R1 plus A naught T1 T2 R2 e to the power by 2 delta plus 5 to the power I 3 delta. Delta is the extra path traveled here for reflection delta is this path, extra path. Not extra path, this is round phase shift due to this extra path. So this is called RTPS. This is round trip phase shift. We know the extra path is we can like this is theta r, so this is d, so this path will be d cos theta r and double, so 2d cos theta r, so delta will be k into 2d cos theta r. It as a common 0 r1 plus t1 t2 or I delta 1 plus e to the power I delta plus r2 to the power 4 to the power 2 I delta and r2 6 e to the power I3 delta and so on. Now we can use the relation for geometrical progression, which is t1 2 to the power I delta into 1 minus r2 square. The term which is being multiplied each time is r2 square into the power I delta. So 1 t2 r2 to the power I delta by 1 minus r2 square e to the power I delta. Already seen r1 is equal to minus r2 p1 p2 equal to 1 minus r1 square. R1 square is equal to R2 square can be written as R, which is the reflectivity at each transference. T1, T2 can be written as tau. So tau is equal to 1 minus R. Putting those value, we'll get here that AR by A naught will be equal to R1 1 minus R e to the power I delta by 1 minus R to the power I delta. Be careful that in the here is 1 minus R, the whole is in the first bracket. The whole thing is being multiplied by e to the power I delta, but here only R is being multiplied by I delta. This can be written as reflectivity, which is AR by A naught whole square. And this is reflectivity at each interference. It is the total reflectivity. Let me write total reflectivity of fabric journal. This is only reflectivity at interface. Same for the transmittivity. So this will be R 1 minus E by 1 minus R e to the power I delta whole square. After the simplification, let me do the simplification in all. This will be R 1 minus cos delta whole square plus sin square delta 1 minus R cos delta whole square plus R square sin square delta e to the power I delta is equal to cos delta plus I sin delta. Putting that value, eliminate that from the uh, denominator, we get this. So this will be 4R sine square delta by 2 by 1 minus R whole square plus 4R sine square delta by 2. So this R, which is the reflectivity of the Favourable Italian, is F sine square delta by 2 by 1 plus F sine square delta by 2, where F is 4R by 1 minus R. If F is called coefficient of fineness. Okay. So one can see when R is less than 1, F is small, and activity is proportional to sine square delta by 2. Delta I have already mentioned, it is K into 2 dn2 cos theta r. It's 4 pi by lambda d n of the cos theta. Now we want to calculate the resultant transmitted. Is A T, which will be A naught P1 P2 plus A naught P1 T2 up to square e to the power I delta plus M naught P1 P2 up to the power 4 e to the power I 2 delta. So, so you can take polynomial as either P1 P2 1 plus R2 square e to the power I delta plus R to the power 4 e to the power 2I delta and this would be A0 T1 T2 1 minus by 1 minus R square e to the power I delta. So we have A0 it is can by written 1 minus R 1 minus R e to the power I delta transmittivity of the favorably favored will be A by A naught whole square, which is 1 minus R whole square by 1 minus R cos delta whole square plus R square sin square delta. Last, this will be sin square delta by 2. So, another thing, transmission will be 1, which means that whatever goes inside the favorable internal, we get outside is same. When f sin square delta by 2 will be 0, which is means sin square delta by 2 should be 0. So delta need to be 2m pi. M can be 1, 2, 3, and so on. So if you draw transmittivity, the one, and this is delta, you will get big certain delta 2 pi, 4 pi, 6 pi, and all. Now we want to know that this width. So what will be the width? FWHM full width at half maxima. Maxima is 1, half maxima. Maxima is when t is equal to 1. Half maxima is t is equal to half. So t is equal to half means if sine square delta by 2 needs to be 1. For that, delta needs to be 2m pi plus minus delta by 2. When we put that, it's going to 2m pi plus minus delta by 2 by 2, which is basically f sine square delta by 4, this is equal to 1. This quantity delta d is FW H. Delta is almost 4 by root f. Okay, the delta is so small that sine square delta by 4 can be written delta by 4 whole square. So if delta 4 whole square is equal to 1, from that this comes. Delta lambda. Delta lambda is 4 by root f. F is fineness coefficient. So if f is small, delta will be large. If is increasing, delta lambda will decrease, which means the peak will be sharper. Okay. Another thing I want to draw that we have seen that the is our So it is if it is f is equal to 400 for f increase reduced to 100, it will be like this. So when f decrease, delta lambda increase. So the peak will become broadened. Okay. We want to discuss the modes of fabric variable parameter. There are polychromatic beam incident normally on favorable Italian with air between the reflecting plates. Okay. In terms of frequency, new variable seems lambda zero. But equation we know that delta equal to 4 pi by lambda in d cos theta r. So when light falls normally, theta r is equal to 0. Okay. I've already seen that so cos theta r is equal to 1. And we have assumed that a echelon is in the medium between the plates is air. So N2 is equal to 1. Transmission transmission resonance happen when delta is equal to 2m pi. So delta, which is 4 pi lambda nd, Actually 2 and 5. Okay. Mu is C by lambda. So lambda C by mu 5 to C by mu is equal to n. Here n is equal to 1 and 2, right? So 2C mu d by l equal to n. So mu will be sorry lambda 4 pi lambda 2 into d by lambda. So d by lambda 2d c into mu is equal to 10. So m will be mc by 2d. Okay. So n is an integer. The above equation represents the different modes, longitudinal modes of the fabricated cavity. For say in mu is maximum because we get transmittivity resonance there. So this equation represents longitudinal modes of fabricated Italy. Okay. Now, my example. E is equal to 10 centimeter. So what will be the frequency spacing? But if n to 1, then min max is equal to mc by 2md. It's not if, just when. So the spacing or node spacing. So new max or say new m mc by 2d. So new m plus 1. This is mth mode. M plus 1th mode is m plus 1 c by 2d. So there is a new to this c by 2d. Okay. So here frequency spacing just this will be very clear. We see 3 into 10 to the power 8 equal 2 into d is equal to 10 centimeter. So 10 into this is second inverse, which is hertz. So 1.5 10 to the power 7 plus 2 9.5 to 10 to the power 9 second inverse. So this is this 1500 megahertz. So for a 10 centimeter Fabry-Perot the frequency spacing is 1500 megahertz. Okay. And the separation between the maxima for the separation between the between the peak values delta phi by FWHN. Delta phi you have seen is to 2 pi. At 2 pi interval, the peaks get occur. So, so delta phi will be 2 pi by 4 pi root f. This will be pi root f by 2 root f is equal to r by 1 minus r. So, r by 1 minus r square. So, this will be pi by 2 root r 1 minus r. So, pi root r 1 minus r. Separation between the peak values. The separation between the maxima in terms of frequency is given by delta nu C by 2D, or Fn from n till nu FWHM. For each of this maximum will be del nu by F, which is 1 by F C to NB. So C 1 minus R 2 by N D root R. Now we can say maximum, minimum. Okay, sorry. This is minimum that is another thing. No, one more thing, you remember that F is a coefficient of finesse, not finesse. Finesse is another thing. Finesse, let me tell you. This will be cube. The quality factor will be mu 0 by delta nu F WHN, which will be 2 by N D R1 R2 1 by 4 mu naught by C 1 minus R1 R2 by half. Okay, here R is written as R1 R2 root. Okay, if this coefficient of fineness of finesse, and this is called finesse, which is between two mates, how many delta mu can be accommodated. This is delta mu. is between two peaks, distance is 2 pi by delta mu, which is pi root f by 2. Yes. Now, another example is like determine the mode numbers at the extreme ends of the optical frequency region for following examples. Wavelength of 700 nanometer in the rod in red and a spacing of b 2.35 meter. Wavelength of 400 nanometer in the blue a spacing of 0.4 meter. So optical frequency range, one, the extreme range means so the question is determine the mode number of the extreme ends of the optical frequency region of the following example. So the here the optical frequency range they consider is from blue to red. So the one we solve, then mode number, we need to calculate the mode number. This equation we have already find that 2d lambda is equal to m or from this equation 2n d by lambda is equal to m. So m is equal to 2 n here 1 millimeter. So d here is 0.35 and lambda is 700 nanometer. So 7 10 to the power minus 9. So this will give us 0.7 by 700 into 10 to the power minus 9. So it will be 1 10 to the power 6. The mode number will be that. for red light. For blue light, same M returns name them M1 and M2 just to in my lambda where this one d is equal to 0.4 meter, lambda is equal to 400 nanometer. So this will be 2 into 4 into 10 to the power minus 8, 4 into 10 to the power minus 7, 2 into 10 to the power 6. So the mode number for the red light is 1 lakh and mode numbers for blue light is almost 2 lakhs. Another example for an incident being new. So new is equal to 6 into the power 14 hertz. What will be the mode number? Okay. And age is like age, not age. And the spacing between the mirrors are 10 centimeter. So we have calculated mu n is equal to MC to H up to D. D here 10 centimeter to 0.1 meter. Mu here 6 into 10 to the power 14 second inverse. So n will be 2 into D into mu by C. 6.1 into 6 into 10 to the power 14, 3 into 10 to the power 8. This is 2 into 6 by 3, 40 into the power 8. With half. And if they extend the question saying that new values within a spectral width 7,000 megahertz, then what will be the mode numbers? So we have new. So delta new plus minus delta new. Delta new here is 7,000 megahertz. Okay. Then plus minus 2 delta new. So if you add 7,000. 16 to 10 to the power 14. So try to calculate. Sorry, this is not that. Spectral width of 7,000 megahertz means if this is 6 into 10 to the power 14 hertz, this is a boundary, and this is 7,000 megahertz. For It's 6 into 10 to the power 10, 14 hertz. And there is a boundary and this is a boundary and this is 7,000 megahertz. For n is equal to 10 centimeter, between the maximum delta mean is equal to c by 2d. We have seen that. And this is equal to 3 into 10 to the power 8, 3 into 0.1, which is equal to about 1500 megahertz. So m is equal to 40,000 for frequency 6 into 10 to the power 14 hertz. So 39999, it's 4 lakh. So corresponding this new naught is 6 into 10 to the power 14 minus 115 megahertz. And m is equal to 3, 1, 2, 3, 4, 8 hertz. And dash dash will be 6 into 10 to the power 14 minus 3000 megahertz. M is equal to 39997. Will be 6 into 10 to the power 14 by 4 megahertz. Corresponding to the upper end, M is equal to 4 potential 1. Is then now 1. Will be 6 into 10 to the power 14 into 1500. And for it will be 6 into 10 to the power 14 plus 3000. And so let's see correspond to 6 into 10 to the power 14 megahertz. But see, this and this will give 9,000 megahertz spectral width minus 2 plus 14 megahertz. We are asked to calculate for 7,000 megahertz spectral width. So 3,997 and 4 lakh 3 will not contribute to the 7,000 megahertz spectral width. Only with 3 This is how you can like calculate this without the calculator. Otherwise, you can like minus the frequency from 6 into 10 to the 14 hertz and then calculate corresponding m to that. So you need a very precise calculator for that. So now the spectrum corresponding to this question. Okay, and this will be the other. So this gap are 1 megahertz. And this is 6 into 10 to the power 14. Now we will solve a question for variable terms. 0.98 angstrom. So, my previous occur. This is the question. So, the most interesting application of heavy period ethanol is actually application of or benefits of heavy period ethanol. This is nothing to do in longitudinal modes and all those things, but as we have discussed the heavy period ethanol, I am like it is all in the optics to resolve two fields. Here we can see that it can resolve 5,000 angstrom and 4,998.98. Okay. So F is equal to 400, which means 4R by 1 minus R whole square is equal to 400. So here from R will be 0.905. So 90.55%. Okay. So we have seen that delta needs to be 2 and pi. Right. 2 and pi. Delta is equal to 4 pi by lambda m2 b cos theta. It's 2 and pi. So cos theta is equal to m lambda naught by 2 into d. And lambda is equal to 5,000 angstrom 10 to the power minus 10. 2 into is equal to 1. H is 10 into 10 to the power minus 2 centimeter. Okay. 4 into 10 into 10 to the power minus 2. So this will be n 40,000. The relation of F and R, F is equal to 400 in this corresponding to R is equal to 90%. And this is not relevant to this problem. Okay. So theta is equal to cos inverse m by 50,000. Okay. So for m is equal to 1, 2, 3, and all that. And so on. Right fingers will fall at theta is equal to 0 degree, also 0, 0.405 degree, 0.573 degree, 0.702 degree. for lambda is equal to 998.98 angstrom, theta 2 dash will be cos inverse n by 40,000.16. So theta right fringes for this lambda is equal to 4998.98 angstrom will occur at 0.162 degree, 0.436 degree, and 0.595 degree. Okay. Point 595 degree. So corresponding aims are if we put m is equal to 0 or 1, that will give us like an angle about 90 degree and all. But we need angle from 0 degree. So m is equal to, we need to put m is equal to 40,000 first. So that will correspond to 0 degree. 399, that will be correspond to 0.405. 39998 corresponds to 0.563 and so on. Here also, as we have put for 40,000 there, and later start the same notes in the second time also, you can see that and the bright fringes will occur at different angles. For lambda is equal to 5,000 angstrom, thetas are 0 degree, 0.405 degree, 0.573 degree, 0.702 degree, and so on. For lambda is equal to 4,998.98 angstrom, we give bright fringes at 0.162 degree, 0.436 degree, and 0.595 degree. So bright fringes occur at different places. So by this, we can distinguish two different wavelengths. So that is today. We will continue the next day.